First, I thank organizers for the opportunity. My title is Relative Log Poincaré Duality. Plan is first I review some classical statements. And next, Poincaré duality in log-betted cohomology, and third, log-etal cohomology. And the notation throughout the lecture, A denote a ring, D is non-negative integer, and curly form is in the derived sense. Okay. First, let F is a continuous map of locally compact topological space. Submersive with respect to the dimensional topological manifold, which means the upper space is locally the product of the lower space and the d-dimensional topological space. Then for any f and g, we have this Poincaré duality, and where this is a relative orientation shift, and which is locally isomorphic the pullback. As a corollary, we have a following statement. And let F be a morphism of complex analytic space, smooth of relative dimension D, then since complex manifold always orientable canonically, sorry, we have this type of duality. So, okay.
Maybe you should add the bracket D also, because you work with D. So.
Sorry?
On the left, maybe bracket D or take twist. Yeah.
There's no take twist.
But you could put, well, 2 pi Z to the D. Yes.
We're at parenthesis, D, not bracket.
Yes, parenthesis D. Yes.
The algebraic corresponding in a dual site. The same statement, same formula holds. Okay. Want analogs of 0.1 and 0.2 in log geometry. This is the subject of today's lecture. Okay. Now, oh, sorry. Is it okay? Yeah. Oh, sorry. Section 1. And first, we explain the generalization of 0.1. Okay. This is the geometry and topology. SS log analytic space. Vertical, exact, and log smooth. Exact, recall that exact means this is a Cartesian. And and any fiber of f log is which is topological manifold as explained soon. And this fiber is of dimension 2D. Then we have this is a correct statement. Yeah. I explained the some briefly the proof. This theorem is based on the rounding theorem. And this means f log is submersive with respect to even dimensional topological manifold. To show an essence, we consider an easy, simplest example. Consider the diagonal homomorphism from n to n square. Then our f is sorry. The standard log plane to standard log line. Then if we consider the associated real blow-up space, then the upper space is circle, cross, circle, cross, this one. And the map is multiplication. Then the picture is as follows. And this fiber is this fiber is this, and the special fiber is broken but homeomorphic to general fiber. So then there is a homomorphism. Like this. So corner is rounded. Then apply Peltier's 0.0 for this map and care orientation. Then we get 1.1. This joint work with Arthur is one of most exciting and fascinating experience in my life. I explain why. Of course, it is a great honor for me to co-work with Professor August, but more. We know, in general, in a joint work, contribution or role of each author is not necessarily the same. Sometimes an author does little, another does almost all. An author only gives an idea, another only gives proofs, another only writes down, and so on. But in this joint work, I feel our contributions were exactly 50-50 because we enjoyed all steps of study together, starting with simple example, this one, and proceeding to more complicated ones, discussing proofs, generalizations, and how to write them up. So I thank my God to arrange such a nice collaboration. Thank you. Now, I proceed to the L-adic analog, which is analog to theorem 0.2.
So if you don't assume vertical, you will have manifold with boundary, I suppose.
Correct.
But if you don't assume, then you have manifold with boundary or something
Yes.
like that.
Yes.
And then there is still Poincaré duality with using extension by zero from the interior.
In that paper, non-vertical case is also treated, and then this is modified. That is another story. Okay. Today, for simplicity, I restricted all things under the vertical assumption. There are two kinds of log-eta cohomology. Both are due to Professor Kato. I briefly review the definition. And let X be an FS log scheme. The first one is a ket site. Object is Kummer and log-eta. I don't give the definition of Kummer-ness, but it is equivalent to exact and log-eta. And the definition of exactness is already given. Typical ket covering is is such a thing. Among two variants of log-eta cohomology, this ket definition is more similar to the usual eta site. For example, ket map is an always open map. Another site is a full log eta site. Object is all log eta, and covering is covering covering surjective family. Universally surjective family.
It's because exact trajectory back is universal trajectory, but that exactly is not true anymore, right?
Exact exact plus surjective.
So it is all in the FS, the category of FS log structures.
Yeah.
So
FS.
all the fiber products, okay. Yeah.
Fiber product can be empty. And the difference lies in log blow-up. Which is log eta and universally surjective, but not exact, not necessarily exact. The typical example is like this.
Am I right? If you leave out one of the strict transforms, then it's no longer universally surjective. Is that right?
Oh, so if we remove some point, then it is not universally surjective because the base change of the same thing. Base change is so. This is the open immersion, but not surjective. There is a morphism of topoid from full log to ket. this is and lemma 2.1 exactification. Assume the source is quasi-compact and target has a chat, then in FS log scheme. Then there is a log blow up of the base so that the base change is exact.
Frame is enough?
Sorry?
Is it enough to have a frame rather than a chart? Do you happen to know?
Frame. Frame is enough, I think. And as a corollary of this 2.1, full log getter topology generated by ket topology and log blowups. The next lemma is pull back and push forward, then we have the original one. And push forward by kappa and pull back by exact F commute. And third, it's a change of the role of kappa and F under the assumption exactness. Okay, and more let P be a log blow up. In the ket side, in the ket context, this is by Fujiwara Kato. And further, if F is locally constant and constructible, sheaf of A module, then push and pull back is the same as original one, and push forward is also locally constant and constructible. And about the full log getter, the situation is much better. That is, this gives an equivalence of topology. Using these propositions, we can prove various fundamental results explained soon. by going from ket to full and vice versa. By exactify the by log blow up and do with log blow up with this proportion. And under the exactness, we can use this proportion and so on. Now I have to explain fundamental theorems. I want to 10 theorem. Sorry. No. Much. Ket, let, proper base change, smooth base change, proper smooth base change, cohomological dimension 2. Okay. More theorem today these are all necessary, but finitude or
It's difficult to read what you write in this part of the work.
difficult.
Yeah, because there are the shadows.
So, proper base change, what was the next one I forgot? Smooth base change?
What did you write above?
Proper smooth base change?
Looks like coolness. Coolness.
And not. And something new and something old. This is new and this are new. And published one is this and this only two. And this 4 theorem due to Professor Kato. And where I explain.
What did you say? Not what?
Not naive. Where not naive means falls under the condition as some a strange condition as follows. Consider the concerned Cartesian. Take any point. Consider this homomorphisms of monoids. And the condition is any element of the associated group of this monoid if F group of A belongs to M bar and G group of A belongs M bar inverse, then A is trivial. Under this condition, proper base change and smooth base change, ket proper base change and ket SBC holds under this condition. And this is, in a sense, best possible. Not only sufficient, but also necessary condition. And other statements holds naively with no problem. And we remark of the condition star first. Either F or G is exact, then this condition holds. So under the exactness condition, we can freely use every base change theorem. Next, if condition, if sorry?
A base change of exact is still exact?
Yes.
Yeah. If Cartesian diagram D in Fs log analytic space satisfies obvious analog of this condition, then D log in topological space is also Cartesian. This is published. So it seems a rather strange condition, but something related to a good geometry. And CD1. Sorry. There is. CD1 is the following statement. Let F is compactifiable. This means underlying is compactifiable in Fs log scheme A torsion, and let D is a relative dimension and let R is relative log rank, then cohomological dimension is 2D plus R. This is a ket in the ket context, and 2D plus 2R in the let context. And this is sharp.
How will you define proper support direct image? Because the compactification is only a scheme, it's not a log.
Compact. Okay. So this is a definition. And CD2. Assume further that f is log flat and locally finite presentation. Fiber dimension is D. Then we can drop R. Of course, there is no time to explain the proof. So I only state the give the structure of the proof. Structure of proof. And PSBC is rather complicated. So log let PBC plus let SBC implies ket exact PSBC, and this implies let PSBC, and finally this implies ket PSBC in general, like that.
People might be surprised to know that a log blow-up is log flat.
No.
Log blow-up is log flat. People might be surprised to know that.
Log blow-up, log flat. Sorry, what is your
Log
question?
blow-up is log flat, right?
Yeah.
Yeah, people might be surprised to hear that. So. So now we come to sorry.
これでいいのかな。State the main theorem. Oh, more 14 minutes. Vertical, proper, logarithms, any fiber equity dimensional. RF, this that the advantage is that base is arbitrary, but clearly there are some problems. Properness shouldn't be, of course. So problem 1, non-locally constant f and non-proper f. This is okay for the case where y is a standard log point. This is an odd result, 1997. This is proved by embedding x locally into a logarithms, log regular, logarithms. So embedding x as a log locus into a toric variety and calculate explicitly.
Want to take RF low Schrick in the non-proper case or RF low? Is it like a Poincaré duality, so with RF low Schrick?
On the right hand side, it should be a floor shape, maybe.
Yeah. Okay. And problem 2, non-vertical case. This is a different story, and I don't I don't give no more comment. And I outline of the proof
This is for the cat or for which étal topology it is? For the usual or for the cat topology or the full étal topology?
Both. Yeah. Sorry. Step 1. Assume F is saturated. So the main difficulty is to construct trace homomorphism. And there are 3 steps. First, assume F is saturated. Consider the diagram. Cartesian. Forgetting log. Okay. And then consider the Ray spectral sequence, this composition. Then, since epsilon is saturated, then R epsilon 0 star lambda is lambda. And cohomological dimension E to PQ equals 0 if P not only cohomological dimension, but also some. Only this is okay. And then anyway, these terms are vanished. So the E2 term only lives here. So see this point. Then vector sequence gives E to 2D0 to the this to dimension. Then this is the surjection, and by proper base change, by proper base change. This is the pullback of the push forward of this. So epsilon lower star, upper star. Then this is classical étal cohomology. So classical trace in SJ4. We have. Then we can prove that this morphism factors that surjection. This factorization is very non-trivial, but by proper base change again reduce to case 4.2. So step 2, f is exact. Then take a ket cover such that f dash, f prime is saturated. Then the underlying of these Cartesian is also Cartesian. Then trace for a f prime group, because the classical trace for f prime is constructed by classical one. So the classically Cartesian, under classical Cartesian, they behave well. And finally, so general case reduced to exact case by log blow up. Oh, there's no time. So, thus we have trace morphism. And by adjoint, and this should be an isomorphism. Then problem 1 is to be fixed, but I have no idea to prove this is an isomorphism for the present. Anyway, by formal duality in ket, this gives an homomorphism in the statement. To prove it, it is an isomorphism. First ket exact case by PSBC, both sides are locally constant constructive. And then by PBC, reduced to log point base case. And applying capacitor, then let exact case. And finally, again by log blow up, we have the general case. Thank you very much.
Are there questions for Professor Nakayama?
So the technical question on step 2, if you want to make an exact guy into saturated, why you say that Kummer et al. Is enough? Maybe you have to take roots, not prime to p. I did think this is needed to give an integral map, and no, not integral, something Q integral, you want to make it integral. I'm not sure about this, but
I forgot the detail, but it is possible. One day I have the same question and the preprint has a gap, but somehow it is fixed, so we can discuss later. So.
Are there other questions?
Louis.
Or just general questions. When you try to imitate the proof in GA4, so if an F trace has a formal right adjoint, and then try to estimate, to calculate F trace in nice cases. So basically maybe pulling the discount in isomorphism. So what goes wrong? Why the naive imitation of SGA4 doesn't work? So this is a basic point about duality. I think SGA4 is about reduction to curves, and you have the use duality of curves and some effaceability property. You use something on pi1, and so yeah, and here maybe you could find the curves. I don't know. So what goes wrong? Why do you take this sort of complicated path?
This already the problem in log point based case. So
But you have hope.
Perhaps there's no good vibration in logisms.
See, you have the Young, you have the stable curves.
Anyway,
I just wondered if you could write a simple example where star isn't satisfied.
Star is satisfied.
Yeah, where a simple example where it's not satisfied.
Not satisfied. Not satisfied. For example, log graph and log graph is
One more question. One more question. So the global duality. So any hope for local one?
Local one? In which mean?
I mean, dualizing complexes.
Dualizing complex. So it is a problem. Yeah.
If there are no more questions, let's thank Professor Nakayama again.